So what we are going to look at today is towards half of it would be state space models, but more importantly, we'll see something called differential equations to start with. So is there somebody here who's not seen a differential equation? Yeah. So when you think of a differential equation, what do you think? Other than this crazy math, I don't want the math. So other than that, what do you think of a differential equation? I'd like responses. Why do you even need differential equations? What does, I'm not going into the math, what does a differential equation give me?
It helps us to capture dynamics like a spring mass system.
Okay. So he says it will help us to capture dynamics, that's fine. Okay, and he talks of a spring mass system, so he's definitely a tuned engineer. He thinks in spring mass and RLC circuits, etc. But I'd like to look at differential equations as one way of modeling, or rather, describing the evolution of anything which is changing with time. Take mechanical systems, aerospace systems, economic systems, biological systems, all of them, right? Systems which change with time is what differential equations give us. So when we learn differential equations, how do we learn it the first time? When did you first encounter differential equations? Would it be safe if I said 10th standard? Or is it later? 10th is safe? Or okay. What was the first thing you learned about differential equations once somebody told you, gave you this, I'll use the red. So suppose there was something like this. Right? You were given something like this. What more information were you given? dx by dt equals x. So what you were told is that there is x is a dependent variable. I'll necessarily have to cover one side, but I'm sorry, I can't help it, of an independent variable called time. And what you were interested in is how x changes with time. But you were given something very important. What is it that I'm missing out? Perfect. You were given something called an initial condition. So that was, let's call it time 0 was some x naught. Okay. Then what did you do? In your first course, somebody described this. They gave you an initial condition. Then what did they tell you? Which I think most Indian students in science and engineering are very adept at doing. They asked you to find a solution to the differential equation. Am I correct? Right? Most of the time you are concerned with a solution to the differential equation. What if you could not find a solution to the differential equation? This is simple, dx by dt equals x, I'll get a solution. But suppose I had something more complicated. Sine x, x plus maybe x squared. I had something more complicated. I don't want to spend my life solving that differential equation. It doesn't really interest me at all. However, I still want to know because it represents some system of great relevance to me. So how do I go about understanding it, right? So then I get something called a qualitative picture of a differential equation. So let's just go ahead. So my talk today will be split into maybe 3 modules. The first module is talking about the qualitative behavior of differential equations, which is extremely important. I'll highlight that. Then I'll describe a little bit about what is called converting those to a state space model. And then I'll talk of a technological invention which really spurred the state space model. So I'll do these three things today, and towards the end, we'll do something called Kalman filters. Okay, let's start. Throughout the talk, I'll be very happy if you ask questions. I'll be very happy if you answer questions, however, what people call silly the answer may be. No issues at all. Just, I'd like responses, right? Okay. So this is roughly the outline of my talk. So let's come to when somebody contributed something substantial to differential equations. Okay, this is what I've been saying in the preliminary part, so that's okay. So let's see, without getting into spring mass or resistor, inductor and capacitor type things, let's move away to another world. So what's that other world?
Imagine a population of rabbits in some nice plain field. The sun is shining, there is plenty of food, and they can reproduce as much as they want. But now a small population of foxes appears, and because they find all of those rabbits, they too have plenty of food to reproduce. Now, as more and more foxes appear, the rabbit population diminishes, right until the foxes don't find enough food anymore and stop reproducing. This leads to their population getting smaller.
So there are two populations, a rabbit population and a fox population, and so now the presenter is going to talk about how these populations vary with time and analyze this with the help of differential equations.
And so the rabbits can flourish again, and the cycle repeats. Hi and welcome to Premature Abstraction. Today we dive into the Lotka-Volterra predator-prey model. Let's try to model the situation mathematically. We have the rabbit or prey population. Let's call them X. Now, the more rabbits there are, the faster they reproduce. Therefore, we can say that the rate of change of this population is proportional to the number of rabbits.
So that's the first thing he does. The rate of change of the population of the rabbits is proportional to X.
We don't know with which proportionality constant, so we just choose a constant parameter alpha here. On the other hand, we have the number of foxes or predators, y. And of course, the more foxes there are, the less food each one finds and more starve. So we can also express the rate of change of this population, again with a proportionality constant, but this time with a minus sign in front to show that the population shrinks when left on its own. If we left it at that, the two populations would not interact. The foxes would just die out naturally, and the rabbits would exponentially reproduce. But a fox will hunt the rabbit when it...
So that's the way he plots how the rabbit population, the fox population decreases and the rabbit population increases.
It sees one, and the more foxes or rabbits there are, the more likely it is that two meet. So we can just multiply the two populations to model this. An interaction between rabbits and foxes reduces the growth of the rabbit population and increases the growth of the fox population, again with some proportionality constants. What we have here are the so-called Lotka-Volterra equations. Let's see how they behave when tweaking the parameters.
Okay. So we'll shortly see how that behavior can be depicted in another way, in what is called a face portrait. So let's look at the person who actually came up with this idea of looking at differential equations. This way, that's Henri Poincaré. And his key insight was study the geometry of trajectories rather than solving ordinary differential equations explicitly. So there are lots of other things that he pioneered, but this is a statement of his I like, because often in the way we do math, we get caught up in the nitty-gritty and the tools of things or just facts and figures, but never something bold. So science is built on facts as a house is built of stones, but an accumulation of facts is no more a science than a heap of stones is a house. Okay, so a very, very popular problem which he worked on was the three-body problem. So has anyone here heard of the three-body problem? Yes? And what is special about the three-body problem? A bit louder, please. System is chaotic, perfect. So what he means is, I'll show you the equations, they're already here. So let me just explain this and explain what he said. The system is chaotic. So what this is there are three masses, 1, 2, and 3. So each of them is just being acted on by the gravitational pull of the other. So each of them has two forces, and I leave them. And how do they evolve in time? So when he said something is chaotic, one way of looking at it is, say, suppose I start running from here. If I started here or started here, and I decided to use the same type of strides and gait, I'll be almost close to where I started from, right? But in this system, you could be a little distance away, and this trajectory will be far widely separated. So that's what is one implication of chaos. So what are the equations here? So what you have is just Newton's laws, and you can see that the two masses and the distance between the two masses and the inverse cube law, and for each of them you write down. So each of them is a position in three-dimensional space. So you have each of those positions in three-dimensional space, so you have an 18-dimensional equation. So here's where we'll first use a word called state space. So how many people have heard of state space modeling? So quite a few people. So yes, what is the difference between a differential equation and a state space model? Yourself. The brown t-shirt? Yeah. Yes, yeah. You can sit down, yeah. Okay. Okay, let me put it in sort of a more precise way. It's not representing it in a mathematical way. It's as representing, suppose you had an nth order differential equation. Suppose you had dnx by dtn, like you have d squared x by dt squared or so on, and you had some powers of the derivative on the right-hand side, and so on, right? And maybe it goes up to right? Now one could write this nth order differential equation as a set of n first order differential equations. So you can, instead of having one nth order differential equation, you could write it in terms of, so what he said was something like again a mass spring system. So you have an equation like this. Mass acceleration is some force or a control or an input, and you can say one state is position and one state is velocity. And you could then write this system of equations as x1 dot equals x2. This is dx1 by dt. So you have two first order differential equations. Okay. So most people here come to do projects, or rather many people across engineering colleges would like to do projects or involved in projects on autonomous vehicles, drones, robots, etc., right? So one of the equations that you see is the one written somewhere in between there, which is x dot equals ax plus bu. So the earlier nth order differential equation is this. I'll be sharing my presentation after this, so I'll give it to the sponsors and they will share it with you. So the Poincaré equations for the three-body problem would look like this, as was said here, in terms of a state space of this form, right? Where each of the QIs is got three components. It's in 3 dimensions, right? But most of us see systems like this, x dot equals ax, which is the state space version. But we also see control, which enters the equation, and measurements, which is y. So many of you may have seen this, the state space model and the measurement equation. Okay, so let's get into these later, and let's just have one look at how 30 simulations run in parallel of the three-body problem, how they evolve in time. So I've got one more video for you. When you go back, you can take a look at this. But for keeping time in mind, I'll show you one. So let's come back to the rabbits and foxes problem. So if you notice that the system had been modeled this way, and so if you plot the predator population, so y is the foxes and x is the prey. We are not talking of a solution of this differential equation. We are talking of portraits which give y and x at any given point of time. So what you see is closed figures like this. What does this indicate? Here, if you go down here, it indicates that the predator population is decreasing, and at a certain point, as it decreases, you also see the prey population increasing. So these form closed orbits. So here's the first qualitative picture of a differential equation, that you can visualize equations like this in terms of such diagrams, which are called face portraits of the dynamical system. So this, again, coming back to the model that I described, these are the Lotka-Volterra equations. Okay, so let's go to, so here's something related to that as well, which is you can qualitatively talk of stable points, unstable points, you can talk of limit cycles. So in this case, you have all these closed figures around a central point. Okay, so that's the first part. That's autonomous systems, initial conditions, evolution of differential equations. Now we'll come to the part which has control in it. So this is the nth order differential equation that we wrote down, but the difference is that now you have a control. You have something, yes. 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 Okay, nice question. So his question is, sir, how do I make those trajectories? Any answers? Suppose I give you suppose I gave you an, let's say there are two variables, x1 function of time, x2 function of time, and I gave you dx1 by dt is some f1 x1 x2, dx2 by dt is f2 x1 x2. Correct? This is the set of differential equations. So his question is, if I'm just given a set of differential equations like this, how do I get those sort of figures? Yes. To do, yes, but okay, let me just, you're partially right, but let me just. So what did those pictures have? They plotted both the variables. They have x2, x1, say the predator, prey, right? Let me take a point. What does a point say? It says just some value of this. So if I call P, P will be some x1 value at P and x2 value at P. Now if you are at P, in order to draw that figure, you will have to say, will the prey population increase, decrease, remain the same, etc. What exactly gives, so basically the question is, if I'm sitting here, will I move like this, will I move like this, will I move like this, will I move like that? Your response was, how would I integrate them when you said that? But in the first place, when I'm given this, how do I find out in which direction I move? That's given by the right-hand side. What is the right-hand side? The right-hand side is, at this point, it will be F1 right? This is a 2 by 1 vector. If I plot this 2 by 1 vector here, I'll get a vector in some direction, right? With this base point, if I plot this, suppose this vector were 1, 2. If this vector were 1, 2, then the x component is 1, the y component is 2, the resultant is moving in this direction. Is that seen? So that gives you, take a simple spring mass damper system, try this out. You'll find out how it moves. Take an RLC circuit, do this. Is that clear, what I did right now? All that I did was, I know this because I know this point. I have a form of this, I have a form of this. That's all I've done. Right? Okay. Okay, so here are some popular state space models that you can see. An RLC electrical circuit, the A, B, C, D. Then you see a spring mass damper, which was mentioned, which is in this form. Then you have a DC motor, which has an electrical side. There's a state, which is the current. There are angular velocity and the angle of rotation of the mechanical shaft. So you have a third order system. And let's skip this slide for, okay, let's keep it for now, but let's ask the question. So you have a continuous time state space model. You want to emulate behavior. The answer was partially given. How do you do it on a computer? You have x dot equals ax plus bu. You want to generate solutions of this. Exactly, you integrate it. So what is the most popular integration technique that maybe MATLAB or one of your packages uses? It's forward Euler integration. All that you do is you take, so that's what this is. So this, it approximates the derivative. The derivative is actually given like this, but it approximates the derivative as saying that you have a small interval of time, you go like this, minus h by h, and therefore x at t plus h is this approximately. Is that clear? Right? And you go ahead like this, and you continue, you discretize this continuous model into this form. Is that okay? Okay. So that is a state space model and how I'm going to compute with a state space model. But that won't work for everything. Now I'll ask you one more question. I think some of the people who have done courses with me maybe have heard of this. So what was the reason state space models became very popular in control, signal processing, communications? Why did they become very popular? Why did state space models become very popular? Even today, you take your CD drives, you take many other gadgets, you have state space based control. Why do you think it was so popular? And from when did it start gaining popularity? Yes. Multiple inputs, multiple outputs, perfect. But what was the technology that spurred state space models? Okay, I'll just show you one slide, then you can. Okay, let's maybe not look at this right now. What came in the 1960s? What was the technology that became rapidly popular from the late 1950s and 1960s? Yes, digital computing, right? So what was the advantage of digital computing? That earlier, if you did something using circuits, diodes, capacitors, resistors, etc., now you could do the same thing as a program, and you could change it as often as you want. There was nothing more that you spent than changing the code, right? There's also another very important problem which state space models helped. What was that? That was the filtering problem. What is the filtering problem? Not students who have gone through filtering with me, but somebody who's not done filtering with me. What was the filtering problem in electrical engineering or mechanical, whatever you choose? What was the filtering problem? Yeah, let me just see if I can get somebody else. 2 or 3 of you have answered, but I'll come back to you. Anybody who wants to take a shot at what was the filtering problem in engineering? Okay, go ahead.
So like estimating the true signal from...
Perfect. Yeah. So here's a signal, let's say with time. This is the true signal. Let's call this maybe S, the true signal. But this is transmitted and I receive it here as Y. So I receive the signal here, but that signal looks like this. From what I receive here, I want to get this. That's filtering. You want to remove the noise or all the erroneous inputs in the signal. So what is the technique that you learn in the process of doing engineering of this? You can build just your filters using capacitors and diodes and other elements, right? But digital computers gave a big boost to this, and that was that you could now do this problem using state space theory. And that was the big technological leap, and what did the first real technology, I should say display of technology due to this digital filter was the Apollo 11 landing on the moon. So let me show you that. So here it is. So this is, pre-1960 approaches, Wiener filter, stationary signal. So this is your true state, your red, and you have noisy measurements, and you want to extract the true signal. It cannot handle time-varying systems, infinite memory. So here's what became very popular. It's called the Kalman filter. So how many people have heard of the Kalman filter? Because a lot of you work on drones and stuff like that. Oh, lots and lots of people. Okay. So for people who raise their hands, I'm going to catch one of you. So tell me how did you do the Kalman filter? Anyone? Anyone? You can just tell me, what did you do in the Kalman filter? Lots of people raising hands. I mean, I wouldn't want to take you again. Anybody? What did you, yes, please. Model the signals using probabilistic models, perfect. And then what did you use it for? Okay, you used it for some application like a drone. What did you use it in the? Estimating the pose, the attitude. Okay, right. And what were the signals you got? X? Okay, all right. Fine. So maybe we'll proceed. So the big breakthrough of state space model in the filtering area was that you could model these signals as the output of a linear dynamical system. You could model this signal, this Y here and this S here. So you could write a state space model like this with noise and a Y which was corrupted, but this is your, let's think of this as yes, S. Let's think of this as S. And from this is all noise here. And from this type of a measurement, you want to find out not only S, you want to find what is X. So that was the problem which was posed and solved by Kalman. Yes. So some advantages is these were recursive, only the current estimate was required, and it was used in the Apollo 11 mission. So the greatest achievement of this, or rather one of the first great achievements of this filter was this, and let's see if I can.
Here today. And thank you very much, and I look forward, all of us look forward to seeing you on the Horn.
I think there's a clipping of the moon landing mission from the NASA website.
Both in the windows. And I can see everything quite clearly. The light. Back to the right about half as much. Okay.
Okay, I will. Okay, so what did it use? It used a Kalman filter to estimate position, velocity, and attitude
Okay, that
in
looks
real
good
time.
there, Neil.
Oops.
Yeah, that looks good there. Okay.
Okay. Now, how does that Kalman filter work? What's the principle on which it works? So let's look at that. So you have a discrete state space model. It's a time 4:45. Where these are the noise sources. So you have noise here. They're all described in terms of Gaussian models. Okay? And the philosophy of the Kalman filter is the following. So if you are at I minus 1 and I, so you are going from stage 0, 1, and so on, you're going here. So if you are at the stage, you could estimate your state. So I'll call the estimate of the state as x hat I or x bar I. What's the difference? So here, I'd call it before the measurement I get at this stage as x bar I minus 1. After I get the measurement, I'll call it x hat I minus 1. And the same way here. Okay. I've got hat and bar. So what bar indicates is at this stage I minus 1, I have still not taken the I minus 1 measurement. I'm relying only on the past measurements. What hat indicates is I have processed this measurement. Now, what do you think should be the philosophy of an estimator which does this? Suppose I'm at stage I. I've got an estimate of what my state is at stage I. I get another piece of information. How do I incorporate it? What if it were erroneous? What if it were a very bad measurement? How do I decide? So the Kalman filter decides that x hat I is the a priori plus something called a Kalman gain, which gets multiplied by so this is the formula for the filter, where it takes a prior estimate and then makes use of the most recent measurement to update the estimate. Do you see that? You have a prior estimate based on what information you had till now, and then you take the current information and update your estimate. So that's the philosophy on which it works. Okay, so I think you will be able to, so this is just a block diagram showing that. So this is the prediction stage. So I have a control input here, which I have not shown here. There's a control input here, and there are certain matrices like P, etc. you see here, which is the covariance. Since you have noise processes, you have a mean and a covariance, so these are propagated. And then you have an update, so you take the most recent measurement. So this is the prediction, which I told you from here to here is a prediction stage. You're not getting more information. Then you get a piece of information. So then the new estimate is your old estimate, exactly what I've written here, and that's the way it's done. Okay, so I have another 5 minutes, and I will just do, okay. State space models. How many of you have heard of controllability and observability? Nobody. There are some very mild hands sort of showing. So anybody, what is controllability? From what the word says, it's very simple. What could controllability mean? Okay, let me ask you this. Say you have a state space model. Let's say I am at the 0 state, x is 0. You tell me you have to go to the state xf using some control. Can you do it? I'm at a state 0. I want to go to some other point. I have a model here. What is it that assures you that you can actually go to that state? You may not be able to go to that state. So that's the property which is studied in state space models called controllability. So that's what I have written, put here. You don't have to worry about some of these other issues. Now there's also another issue. There's something called observability. What do you think observability could be? In a state space model, you are getting measurements. Why? Do you think from these measurements you can find x? If you have a stream of measurements over a finite interval of time, can you find x from these stream of measurements? So that's an issue called observability, which is also addressed in systems. So I've given you in these slides what are the tests for controllability and observability. And I'm pretty much at the end of my presentation, so I'm almost done. I'll be happy to take any questions you have. Anything related to control is fine with me. So the last few slides are just observability and some of the key takeaways of this.